Hello Year 11s. Today we're going to be looking at an introduction to mass defect and binding energy. These concepts are defined in the syllabus to the point that you sort of need to understand what they are and where they come from. And then when we start looking at things like fission and fusion and nuclear reactions, you can apply your knowledge of binding energy and mass defect to determine the energy released in, say, a fission reaction. And that's applying this relationship here, an equation that I'm sure you're very familiar with. So just to recap on something that we talked about earlier in the nuclear physics course, we have what's known as the atomic mass unit. Now, the atomic mass unit is a more convenient way to illustrate masses in nuclear physics because the masses we're dealing with are so small. So one atomic mass unit, according to our data sheet, which is what we're going to be using, is 1.66 times 10 to the negative 27 kilograms. And the mass of a proton and the mass of a neutron on our data sheet is given in kilograms as well, as 1.67 times 10 to the negative 27 kilograms. So if we wanted to then work out what the mass of a proton or a neutron was in terms of atomic mass units, what we would do is we'd say that this is just 1.67 times 10 to the negative 27, and we divide that by what that represents, what one atomic mass unit represents in kilograms. And what we end up with is 1.006024 atomic mass units. And what this means is that for year 11 physics, the mass of a proton and the mass of a neutron are the same, when in reality they're slightly different, and that we now have a way of representing the mass of protons and neutrons with a number that's not so horribly small. It's really important that when you make these calculations, you keep these final digits, you keep as much precision in your answer as possible. What we're about to find out is these tiny bits of leftover mass, or these tiny, or the seemingly tiny changes or differences actually do make a huge effect when you're doing binding energy calculations. So what I'm going to do is start by looking at the mass of helium-4. The mass of helium-4 that I'm giving you, and if you're doing a test, they will actually give you this value straight out, so it's not something that you can find in your formula sheet, is 4.002603 atomic mass units. Now, what I want you to try and do now is, knowing that the mass of a proton is 1.006024 atomic mass units, and the mass of a neutron is the same, so 1.006024 atomic mass units. Use this information to determine what the mass of helium-4 should be if you just got those particles, so 2 protons and 2 neutrons, and you put them together. What would you expect it to be? Now, if you did that, or maybe you just haven't pressed pause, what you would find is that the mass of the 2 protons plus the mass of the 2 neutrons should just be equal to 4 times 1.006024 atomic mass units. Now, if you did that, what you should get out is 4.024096 atomic mass units. Now, importantly, what you would have discovered is that this mass here is not the same as this mass here. So why is this, and what are we looking at here? And this brings us to the idea of the mass defect. So what this tells us is that, or what the hard and fast rule is that the total mass of a stable nucleus is always less than the sum of the masses of its separate protons and neutrons. So if I was to illustrate that, if I had a proton plus a proton to make helium, and then I add the neutrons, and they are going to make, well, if I was to draw some sort of arrow, a helium nucleus, that the mass of these guys is always going to be more than the mass of this, even though when we look at it, it's the same amount of matter. And we call this the mass defect. And I've illustrated down here with a calculation. And the mass defect of the calculation you've just performed is negative 0.021493 atomic mass units. Now, there's a negative there, but just remember that the mass of the stable atom is always going to be less. So that number will always be negative, or if you do the calculation the other way around, it's going to be positive. But negative just sort of indicates that it is a mass defect. So the first problem I want you to have a crack at is the carbon-12 atom. I want you to figure out for me the mass defect of the carbon-12 atom. So if you're watching this video, I would prefer it if you paused it and then had a crack at it. I'm assuming that you've paused it and you've pressed play. So now if we're going to solve this, what we want to do is we just want to find out what are the masses of all the different particles in there. So carbon has 6 protons and 6 neutrons. So it has 12 nucleons. So the mass of the different particles is going to be equal to 12 times 1.006024, and what I end up with is 12.072288 atomic mass units. Now, the mass of carbon-12 is actually just 12 atomic mass units. And the reason this is such a nice clean number is because, remember, the atomic mass unit was derived from the carbon-12 atom. And this is the only situation where you'll end up with this really lovely whole number. So looking closely at that, we can see that we have a mass defect, in this case, of negative 0.072288 atomic mass units. So now we're going to relate the mass defect, which is, again, the difference between the mass of the atom itself and the sum of all of its parts. The missing mass, or the mass that has somehow just disappeared, that represents the binding energy of the atom. So now we're looking at the idea that mass and energy are equivalent. So binding energy is the energy equivalent of the mass defect. So in terms of what binding energy actually is, it is the amount of energy required to take that atom. So if we want to get that carbon-12 atom and we want to separate it out into those components, if we want to get, so maybe I'll use the helium as an example because it's easy to draw, but if I have my helium atom sitting here and I want to get to its components, then remember that these different components actually have more mass than what it has over here. So I need to somehow add mass to this, or add energy to this, to separate it out. So that's why sometimes the binding energy is called the separation energy, because this will not actually move into its components until I can somehow make up that mass defect. So if you want to figure out what that energy is, and you have the mass defect, then you have this really well-known formula. I'm sure you've heard of it. It's Einstein's mass energy equivalence formula. And it's a pretty straightforward one. It's that the energy, or in this case, the binding energy, is going to be equal to the mass, or the mass defect in this case, multiplied by this wonderful constant, which happens to be the speed of light squared. Now, I want to point something out in this equation. When you're dealing with this equation, it's important that you use mass in kilograms and energy in joules. So if you have the mass in atomic mass units, then you're going to be using a different formula, and I'm going to talk about that next. But if you have the mass in kilograms, then this formula is the way to go. Understanding that when you calculate out the energy, the number you get is going to be in joules. So to calculate the binding energy, there are two methods. You have the original method, which is what I spoke about in the previous slide. You can do that if you have the mass in kilograms, and the result that you get will be in joules. Now, there's another method, and it's an easier method, and it also works well if you've got the number in atomic mass units. So if you've got a result in U's, then all you need to do is multiply it by 931. If you multiply that number by 931, you will get an answer that's going to be the energy in mega electron volts, not in joules. So you'll find that also in your formula sheet. that 931 megaelectron volts. So for every atomic mass unit missing, the binding energy is 931 mega electron volts. Now, these two are both energy terms. So if you wanted to convert between them, you can. The conversion is 1.6 times 10 to the negative 19. Okay, so let's do an example. So we remember that we calculated in the previous, in one of the previous slides, we calculated the change in mass, or the mass defect, to be 0.072288 atomic mass units. So based on this, if I ask you to tell me what the binding energy was, how would you solve it? So you pause it and have a crack at it yourself. Now that I'm sure you've paused the video, we can solve it together. Because the question's giving you the mass defect in atomic mass units, it's actually very easy. So the energy is just going to be 931 times 0.7228 atomic mass units, which is 67.3 mega electron volts. It's important that you get those units correct. So solving the problem from atomic mass units to mega electron volts is very, very easy. As a bonus question, can you instead convert your mass defect from atomic mass units to kilograms and then put it into the other equation to get your answer in joules? And then if you're super clever, what I want you to do is convert that number in joules back to a mega electron volts using the idea that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay, now to solve that, the first thing you want to do is work out what the mass in kilograms is. Now you were told that it was 0.07228 atomic mass units. You multiply that. You multiply that by the mass of one atomic mass unit, which is 1.66 times 10 to the negative 27 kilograms, and what you end up with is 1.2 times 10 to the 28 kilograms. So now I've got the mass defect in kilograms. So I can push that into my E equals mc squared equation. So it'll be 1.2 times 10 to the 28 times 3 times 10 to the power of 8. Now don't forget to square it on the outside of the brackets when you put it in your calculator. And if you do, you should get 1.08 times 10 to the negative 11 joules. So now I've got this value in joules, which is great. But the last part of that question, which is probably the trickier one, is if I've got this number in joules, can I convert it to mega electron volts or to electron volts? So remember that 1 EV is going to be equal to 1.6 times 10 to the negative 19 joules. So that means that the energy in electron volts is going to be equal to this number that we got in joules divided by 1.6 times 10 to the negative 19, which is 0.675 times 10 to the power of 8 in my calculator. But if you want to put that in mega electron volts, what you end up getting is 67.5 times 10 to the power of 6, or 67.5 mega electron volts. So you can see that I've converted back, but if I go back and have a look at the previous slide, 67.5 is not the same as 67.3. And this is what I was talking about earlier. Sometimes if you do these conversions, because we're not holding all the precision in the data sheet, you'll sometimes have a small difference when you check your answers. That's nothing to be worried about, because that's expected as we mark it. Okay, and just before we finish, I want to talk about the binding energy per nucleon. So if we actually got the binding energy for that carbon atom, or the binding energy for the helium, and then we divided it by the number of nucleons. So for carbon, we'd divide that number by 12. We can actually plot the binding energy per nucleon, and it comes up with some really interesting results. What you find is that as you go from sort of the lighter elements and move into heavier elements, the binding energy per nucleon increases until you reach iron. Now, you might remember from year 10 that iron is that point at which sort of a sun starts to die. And that's because fusion doesn't really occur beyond that particular element. And as you'd expect, the graph then starts to decrease at a slower rate as you get closer and closer to, say, uranium, for example. Now, what this represents is that when you have these nuclear reactions taking place, you can sort of figure out what the mass defect will be, whether it be positive or whether it be negative when you say moving from uranium to krypton and barium, for example. There's going to be some leftover energy when that split happens because this graph tells us so. So fission essentially can only happen on this portion of the graph, so in the box that I've marked with fission, because that's where the energy difference is possible when you're breaking it up into smaller components. And likewise, with fusion, when you're combining these particles together, you end up with some leftover energy, and that is the energy that's released after a fusion reaction. And that's why you can't say, well, you can, but this requires more energy to, say, split up helium into, deuterium and tritium. But this graph here is really important because we're not necessarily using this, but this illustrates the idea of fission and fusion, which we're going to be covering in the next topic.